Let's look at the case for series reactions occurring in a continuous stirred tank reactor. So here's the situation. We have a feed of pure A at a concentration Ca0 and a volumetric flow rate V0. And we have first order irreversible reactions occurring in series. So A going to B with a rate constant K1 and B going to C with a rate constant K2. And so these are elementary reactions as written, so they're both first order. So let's also assume here that we have constant density. So our volumetric flow rate is constant from the inlet to the outlet of the reactor. So we can write our mole balances on each species. And so here we're going to try and get concentration profiles for A, B, and C as a function of reactor volume or residence time. So starting with the mole balance on A, we can write the molar flow rate of A entering the reactor, which I'll write as the volumetric flow rate times the concentration, minus the volumetric flow rate at the outlet, and again we have constant volumetric flow rate here, plus the rate of generation of A by reaction within the reactor volume, which is just minus kCa times the reactor volume. And so we can insert the residence time as the reactor volume divided by the volumetric flow rate to get an expression that looks like this. We can write Ca0 minus Ca is equal to tau times K1 times Ca. So now we can solve this expression for Ca explicitly and get a concentration of A as a function of residence time, which is Ca0 plus over 1 plus K1 times tau. Okay, so that's our concentration of A. So for B, we can write a similar mole balance. So the molar flow rate of B in is the volumetric flow rate times the concentration, but we said we had no B in our feed, so that term is just 0. We have B flowing out of the reactor, so that's V0 times the concentration of B either in the reactor or at the outlet, as these concentrations are equal, plus the rate of generation of B. So we have generation from the first reaction, which depends on first reaction rate constant K1 times the concentration of A times the reactor volume minus that second reaction which consumes B to form C. Okay, so we can now insert our expression for the concentration of A into our mole balance for B. So this will look something like this. We'll have the volumetric flow rate either entering or leaving the reactor times the concentration of B, plus here we will insert that expression for Ca. And then we have our second rate of reaction here. Okay, so once again we can solve explicitly for Cb, and that expression looks something like this. The numerator is K1 Ca0 times tau divided by the product of 1 plus K1 tau times 1 plus K2 tau. So to write the concentration of C, we could solve the mole balance as we did for B, but we can also notice from stoichiometry that the changing concentration of A, so Ca0 minus Ca, is either going to be accounted for by an increase in concentration of B or an increase in concentration of C. So just from that stoichiometry, we can write the concentration of C. So this is going to come out to K1, K2 times tau squared times Ca0 divided by the same denominator we had for Cb, so 1 plus K1 tau times 1 plus K2 tau. So we can plot the concentration profiles for each species. So here these are plotted normalized to the inlet concentration of A versus the dimensionless time, K1 tau. So again, for CA, this is going to be a monotonically decreasing function as A is converted to B in this first order reaction. The concentration profile of B, it's going to increase initially as A is converted to B, but eventually decrease as B continues to be converted into the final product C. And the concentration profile for C, initially it's going to have a quite low concentration as there's not enough B in the reactor to form any C, but eventually it will become the dominant product. So like we did for the plug flow reactor, we can find the residence time needed to maximize the yield of B by looking for this maximum, so setting dCB d tau equal to 0, and then solving for tau to get here solve for tau equals tau max. And if we do that, we get that tau max is equal to 1 over K1 times K2 to the 1/2 power. And the yield at this point we can also write as, so the yield of B we'll write as the concentration of B at that residence time, tau equals tau max, divided by CA naught. So how much B did we make relative to how much A we started with? And this is going to be equal to the first rate constant K1 divided by K1 to the 1/2 plus K2 to the 1/2, that quantity squared. So these are our expressions for maximizing either the concentration or yield of B for a series reaction A goes to B goes to C taking place in a continuous stirred tank reactor.